Hey everybody, this is Larry. This is day one of the July. Is it July? Yeah, July Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. We'll be doing this all the time around. I don't think you can see on stream on screen, but I have a 1186 day streak, so we're gonna keep that going for a month. So hit the follow button, come to Discord, show us your code, and just share things. All right, let's take a look. Today's problem is 2305, fair distribution of cookies. So you're given an integer array cookies, where cookies to buy is the number of cookies in the ith bag. You're also given an integer k that denotes the number of children to distribute all the cookies in the same bag. Okay, so you have to do unfairness of a distribution, maximum total cookies obtained by a single child. Maximum to okay. Return the minimum unfairness of all distributions. Oh, I was trying to thinking about like what the situation is, but what's k? K is the number of children. Okay, but the answer is that there are only 8 things, right? So I'm already thinking about some sort of brute force. K can be big, but is it really? Because it could be 8 to the 8, and then but a lot of them are symmetric, right? So I'm trying to think. So the most naive thing is that you could do 8 to the 8, basically like a brute force thing. Actually, 8 to 8 is 16 million, so it's not even super bad, but it's going to be still a little bit too slow, especially on Python. But a lot of them are symmetric, right? So I think that's the way that I'm trying to think how to factor that in a little bit. And what I mean by symmetric is just that, like for example, even this one, right? It like given this one is that the first child you getting 31 and the second child you go over 30. If you kind of just reverse it, it'll still be the same thing. But how do I do this one? I mean, 8 to the 8 is probably good enough, but this is still, I mean, it's not gonna be good enough, but it'll be pretty but we need to make like one optimization, I think, and that should be good enough. Let's see, right? I feel like I should know this, but for example, for k, we can make sure that for k is equal to 2, we can make sure that bag 1 is more than bag 2, but I don't know if that makes sense. Huh. Can we do binary search? I don't know that we can do binary search because I don't think that you can greedy on it to do the satisfactory thing. Because then you still need like a DP thing. Maybe 10 to the 5th is pretty. No, yeah, you can do it with K0, right? How do I want to do it? Sorry, friends. I'm kind of struggling with it today, to be honest. I mean, I feel like there's like just one optimization you need to make for this problem, and I'm kind of blanking out on it, to be frank. Oh, I think I'm just being dumb. So basically, yeah, we can just do dynamic programming, right? Basically, we can do like something like get max of. I think the hard part is that you're trying to minimize the max, right? So basically, you have index for the cookies that we're eating, and maybe the bit mask of the things that we used. And okay, I see. Okay, yeah. Oh wow, this is kind of a tricky medium, maybe, because I was thinking directly, or maybe it's just one of those things where you kind of have a strong first inclination, and then you keep on running into things that tells you it will not work, but you can't get your mind out of it. And for me, I had to kind of reboot myself a little bit to kind of get to here, and so I'll go over it, but I'm not. I think the tricky part for me is that I want to go over it while coding, but this is a live thing. But the tricky part is that I don't know if this is quite fast enough. So I guess we'll discover this together, right? So okay, so basically the idea is that yeah, for each. Let me rewrite this actually. Maybe we have like children index and the cookie index. That's not a good idea. Okay, children index and the cookie index, right? Yeah. And then basically k is the number of children. So if is equal to k, then we return 0. And basically the thing that we're trying to do is we want to take a lot of minimum stuff, right? For example, so here we have the cookie index. So okay, best the base case is that this is done for this this children, and we let the next children get it, right? So that means that we have to get max children index plus 1, co-index is equal to 0, so we just start from the 0, and then bit max doesn't change, right? And what is the cost of this? Well, the cost of this, actually I don't know I could do it this way, because I have to keep track of the running total then. Maybe this is a little bit off, so then okay, fine, let's just do index then, right? So this is the current children taking no cookie, and basically, yeah, you basically want to. So this function gets the max of all the other ones, and you want to minimize it over best. And the current, technically, the score would be something like max of this and 0. But because it shouldn't be 0, so that's why we don't do it. And then we don't want to min it over all that. So now we go maybe for mask in range of 1 C, where C is the number of cookies. Wow, this is pretty tough for day 1. Actually, I didn't go over bit mask, and that's my fault. I usually do, but I think I'm a little bit distracted by this problem so far. But I'm going to do a very quick 2-minute tutorial for bit mask. I know this is day 1 of July, and usually I go a little bit deeper, but this one I'm a little bit uncertain about with respect to the time, the run time. So we'll see. But bit mask basically is just a really fancy way or a very efficient way of doing a set of bits, right? And why a set of bits? Well, or a list, or sorry, an array of Boolean values, right? So you can think about array of Boolean values like maybe a used array as you go to false, true, false, false, true, true, or something like this, right? And if you want to write it in a more compressed way, you can maybe say, okay, well, this is forced FT, FFT, TF, right? And this is much shorter visually anyway. Of course, it's not quite, but, and of course, you can maybe just do, 0 and 1. So this is 0, 1, 0, 0, 1, 1, 0, right? And then, of course, so this is an array of, sorry, just to be clear, this is an array of 0, 1, 0, right? Something like this. And of course, you can be like, oh, well, if we have less than 32 bits, say, then we can represent it using one number, because that's just 0, 1. You can use this as a binary number, which maps to a number, right? And of course, then everything else, and then you see fancy operations that are based on it, like used and mask, and some mask is equal to, basically, if you think about it in a bitwise kind of way, and this is where you write a truth table, and because each bits are independent in these bitwise operations, you could do something like 0 is equal to 0, is equal to 0, oops, right? So you have something like that for each all of them. So basically what this is just that you're trying to find the number of bits that are equal to that, right? And so we'll go with some applications as I use them, but that's basically the idea behind bitmask. Okay. So then now we go if mask and bitmask is equal to 0. The reason why, what this is saying is that, okay, so for this mask, if this mask and the used bit mask, let's just go used, say. That means that there's no overlaps, which means that none of them matches here. If that's the case, then we can do best is equal to min, get max, well, min of best, get max, indexed, used, or mask. And this now just flips all the zeros to 1 because we know that they have no overlaps. We're gonna get a max of this, and the number of cookies that are used in this mask, right? So we'll just say C of mask, right? And we have to do that lookup. So then now we return best. But we have to kind of do the lookup. So C is equal to is equal to 0 times this, right? 2 to the power of C. And then now for M in range of 1 to the C, for I in range of C, we do cookies of I, C of M is equal to 0, I guess. C of M, we added cookies of I. If I to wait, whoops. If M is equal to 0, basically this is saying that if the bit is greater, if the bit is set, we add the sum, and that's pretty much it. And then now we get max 0, 0. We have to memorize, but we'll see if this works quickly first. Oh. Maybe it still wants out of thing. Oh, this should be index plus 1, of course. Mess that up. Because there should only be 8 levels of recursion or something, right? Oh, this one too, obviously. Yeah. Alright, well, that's unfortunate. C is okay. Okay, so that looks okay. All the we have to distribute all the bags of cookies. So that means that the base case is not right. So if used is equal to -1, then we return 0. Otherwise, we return infinity, because that means that we still have some cookies left. And that's why the answer is 0, because, well, the best answer, if you don't have to do all the cookies, is just all the answers are 0. So then now we're good. I can't help but say that we've been using a little bit of magic. So let's go over this code in detail in a little bit. And I don't even know if this is fast enough, to be honest. That's the biggest concern. But yeah, so this is saying that for each binary representation, which means this is the power set, right? Because this is just basically let's say the 5 of, or let's say 4 of them, 0 0 0, then and then dot dot dot, and then all the way to 1 1 1 1, right? And basically the idea here is that, okay, this is the set representing none of them are used. This is one of them are used, the first one, right? We're doing least significant bit first, or least significant bit is the 0 index. And that's basically all this loop is doing. It just kind of loops through all the numbers from 0 to all the way to this number, which is 2 to the power of c minus 1. And then for each one, we basically sum it up so that we check, okay, is the ith bit of m a 1? So we go like, okay, is this a 1? If this is a 1, then we sum it up. And basically at the end, we want c sub m is equal to the total number of cookies that is the sum of, some set m, right? It's a bit mask of m. And here, this is basically saying, the base case is just saying if this is all 1s, then we return 0, because that means that we used up all the cookies. Otherwise, we want to return infinity, because it's not a possible case, because we haven't used up all the cookies. Yeah. And then this case is just, okay, this child gets no cookie. And then we move on to the next. I don't know. I don't think that'll give us a good case, but maybe. I don't know, right? But that's just our base case. And here we're saying, okay, if none of the cookies that we want to use in mask is already used, hence it's 0, then we do a recursion thing. We give these cookies to the current child. So that means that we want the max of the remaining, and then that we want to minimize and give it to the current cost. Oh man. And then we minimize that over all the possible set of cookies that we can give this child. Okay, so we're almost done here. Now we have to memorize, otherwise this gets way too expensive. Index can go from 0 to n, or 0 to k, sorry. Yeah, 0 to k. And use can go from 0 to 1 to the 2 to the power of c. So yeah, so we just have to kind of set up that cache. So let's do it. So it has cache is equal to force times 1 for the maybe k. Yeah, k should be okay. Maybe not, but. And this is just a fancy way of saying 2 to the power of c. You can think about it as bit shifting, as yeah. And basically now we go, if has cache of index used, we return the cache of index used. Otherwise, at the end, has cache of index used is equal to true. Cache index used is equal to best. Is it fast enough? Let's see. Yeah, that was pretty fast. We read a lot about complexity, but seems okay. So yeah, what's the complexity here, right? Well, as we said, so total time is just equal to number of inputs times time per input, right? So the number of inputs is O time of k times 2 to the c. Each input takes O of 2 to the c time. So this is going to be O of k times 4 to the c, right? Or 2 to the 2c, if you will. And of course c is 8, so 4 to the 8 times 8 for k is going to be only 500,000, so this is going to be fast enough. But yeah, and for space is just, of course, each input takes O of 1 space, so it's going to be O of k times 2 to the c space. That's all I have for this one. Here's the top with some pre-optimization, and here's the bottom. And that's all I have for this one. Let me know what you think. Yeah, stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.